Okay, the second and third method to calculate um, basically is to calculate the Thevenin resistance if your circuit has dependent sources. If your circuit has dependent sources, then you cannot use the method that we use to calculate the Thevenin resistance, that is to eliminate the independent sources, short circuiting the voltage source and open circuiting the current source, and then combining all the resistors like we did in the last problem. And the reason we cannot do that is your dependent source cannot be eliminated from the circuit when you are calculating the Thevenin equivalent resistance. And since it cannot be eliminated, then it is not going to be possible to calculate, to combine the resistor in series and parallel combination and to get R Thevenin. So if you do have dependent source, you cannot use the combination of resistance method to calculate R Thevenin. Under those conditions, you are going to use method number 2 or method number 3, whichever you find it easy for any specific circuit that you're solving. You're going to choose one of the methods. Now, to calculate your open circuit voltage, that is still going to be the same way um, like you did in the first method. That is, you're going to use circuit laws, whichever is easiest way to implement on the given circuit, and you're going to calculate the open circuit voltage. So I'm gonna start with a circuit with the dependent source, and then we are going to first calculate the open circuit voltage because that is going to be the same whether you're using method 2 or method 3. And then I'm going to use both methods to calculate the Thevenin equivalent resistance. So this is uh, if the circuit has dependent sources Thevenin method method 1 can be used to calculate RThevenin. So method 2 or 3 will be used. So let's go ahead and work on one of the problems. So let's say problem number 2. And our circuit is this. Source, a resistance, current source, and another resistance, a dependent voltage source, another resistance, and we have to connect the load between nodes A and B. That is, we have to find Thevenin equivalent between node A and B. Let's assume this to be ground. This is the dependent source with 2 VR1. This is R4 and R4 is 6 ohms. This is R3, which is 2 ohms. This is the current source I2 with the value 20 milliampere. And this is R2, the value of 4 ohm. And this is R1, on which your dependent source is depending, basically. This is VR1. And this is our input voltage source, independent voltage source, 25 volt. So the first thing we are going to do is we are going to find out the open circuit voltage between nodes A and B. Now you can implement any method that you would like to get VOC. But again, we are going to use the easiest method. In this case, the easiest method is going to be nodal analysis. Observe that, of course, you don't have any current going towards node A. So node A, this is node A, basically it's the same node. And we have to find the voltage at this node. But the current that is passing through R3 is just going to go to VD and R4, whichever direction you want to take that current, but it will be basically a single branch because no current can flow towards the load. We have removed the load, or we did not really put the load, but if the load is here, we have to remove the load and keep those nodes open. So we can assume that we have this node, I can call it node C since we already have A and B. So we can find the voltage at node C, and let's call this VC. And once we have the voltage at node C, and if we know what current is flowing through R3, then we can easily find the node voltage A based upon the direction in which the current is flowing through R3. Either that drop in R3 is going to be added to VC or subtracted from VC based upon the direction of the current that we will take in RC, and we can write down the equation for VA. So let's assume that let's take different directions of current to apply nodal analysis. Let's assume our current is I1 here going towards node C, and this current is I2 already. And let's assume that this current is we can call it I3, I guess, since we have I1, I2, and I3. So if we apply KCL at node C, we can write the KCL equation as I1 going towards I2 going towards, and this is I2 if it is not clear. This is source I2. I made it worse. Clean it up a little. Source I2. So and these two currents are equal to the current that is going away from the node, which is I3. All right, so let's go ahead and write down Ohm's law for I1 is going to be V1 minus VC over R1, V1 minus VC over R1. I2 is given to us, which is 20 milliamperes, so I'm just going to keep it as I2. And I3 is going to be VC minus VD over R3 plus R4. VC minus VD over R3 plus R4. Remember, we discussed that. The position of VD can be switched with R4 since they appear to be in series. So you can easily see that the current that is flowing from node C to node, let's call it D for VD, to node D will simply be VC minus the voltage VD divided by the total resistance in the path of the current, which is R3 plus R4. Okay. So remember, VD, we know that. What is VD? VD is 2 times VR1, and VR1 is V1 minus VC. So VD is basically 2 times V1 minus VC. So let's go ahead and plug that in for VD. Let me just do it here. Oh, I'll just do it on the next line so that nobody can. So I'm going to rewrite this V1 minus VC over R1 plus I2 is equal to VC minus 2 times V1 minus VC over R3 plus R4. VC is the only unknown, so I'm going to keep that on one side and take rest of the stuff to the other side. So I'm going to take this VC on the right side, it's going to become positive, and I'm going to take, we also have another VC, so that's negative 2 VC. So actually, I'm going to combine this as negative, negative, positive, so it's going to be positive 3 VC over R3 plus R4. So 3 VC over R3 plus R4. And then I'm going to take the one on the left hand side, VC over R on the right side. So it's going to become, I'm going to delete VC from here since I already have it outside the square bracket. And that's going to be 1 over R1, which will be coming from VC over R when I take it on the right side. On the left side, which I'm writing actually on the right, but it's on the left side, I'm going to take negative 2V1 on the left side, but I'm writing it on the right side. So I have V1 over R1 plus I2 plus take the negative 2V1 on the other side. So it's going to become 2V1 over R3 plus R4. And from this equation, we can easily find what is the value of VC. So from this equation, VC will be equal to, of course, right-hand side divided by the multiple of VC. So instead of writing it again, I'm just gonna use MATLAB and calculate that. So let's go ahead and do this. And let's assign the values of each component. V1 is 25, R1 is 10, R2 is 4, and I2 is 20 milliampere, R3 is 2, and R4 is 6, and that's about it. So we have all these values. And let's see, my equation is VC is equal to V1 over R1 plus I2 plus 2 times V1 divided by R3 plus R4 divided by 3 divided by R3 plus R4 plus 1 divided by R. I guess, oh, this is incorrect. No, it has to be have a parentheses here. Okay, that's correct. So 3 divided by R3 plus R4 plus 1 over R1 and V1 over R1 plus I2 plus 2V1 divided by R3 plus R4. You can put this in parentheses as well, just to, it's the same thing though. 18.463. So VC is 18.463 volt. Okay. Now, okay, we have VC. So we can calculate VD, which is 2V1 minus VC. And we know I3 is VC minus VD over R3 plus R4 because we do need the value of I3 in order to calculate the node voltage A. So first calculate I3. So VD is 2 times V1 minus VC. Calculate that. VD is 2 times V1 minus VC, 13.074, 13.074 volt, and I3 is VC minus VD over R3 plus R4. So I3 is VC minus VD divided by R3 plus R4. And that's 0.6737 ampere. So let's write this down. 0.6737 ampere. 0.6737. Okay, so now we calculate, therefore VA. All right, so how I'm going to calculate VA? Again, go back to the circuit and see. Current I3 is flowing from C to A. That means the node voltage at node A is higher than the node voltage at node C is higher than the node voltage at node A, because when the current I3 will pass through R3, some voltage is going to be dropped. So the node voltage A is going to be simply VC minus the drop in R3. VC minus the drop in R3. VA is equal to VC minus I3 times R3. 17.116. 17.116 volt, and that's your open circuit or Thevenin voltage. So this is our Thevenin voltage. Now, if either you use method number 2, which I'm going to discuss now, or method number 3 to calculate our Thevenin, the open circuit voltage is going to be found using the regular method. Employ any method which is easier and find the open circuit voltage. So now method number 2 to calculate our Thevenin. All right, in this method, what we do is we short circuit terminals AB. And then we find what is the current that is passing through that short circuit. And once we find that current, then we take the ratio of the open circuit voltage that we just found out, Thevenin voltage, to the short circuit current. And that ratio is going to give us our Thevenin. Now, since we have a voltage source over here, dependent or independent doesn't matter, and a resistor over here. So basically this is a complete circuit. If you have just a passive component here, for example, resistor or inductor or a capacitor or anything, if you put a short circuit in in parallel to a passive components like those, then those components are just going to be eliminated, because no current is going to flow through them. All the current is going to go through the easiest path, which will be short circuit. But since there's a source here and source is supplying current, then source can supply current in this branch. Basically, this is pretty much similar to a circuit that you can draw something like this. Something like this. It will be similar circuit basically. So therefore, we cannot eliminate this branch. Once again, if you do have passive components, and you can see that putting a short circuit in parallel to those passive component, no current is going to go through those passive components, then you can safely eliminate those components, remove them from the circuit. In this case, we cannot do that. So we're just going to put a short circuit over here, and the rest of the circuit is just going to stay the same. And then we're going to use one of the circuit techniques to find the short circuit current. So let's go ahead and do that. I'm going to redraw the circuit. And then I'm going to put a short between A and B. So this is my V1 values are not changing. V1 is the same, R1 is the same, R2 is the same, of course. The only value that can change is VD, because again, when you change the circuit, the voltage drop may change across R1, currents may change. And since VD depends on the voltage drop in R1, therefore the value of VD can change, but other values are going to stay the same because independent sources values are not going to change, of course, and resistor values are not going to change. But VR1 may change. And this is 2VR. And our goal is to find the short circuit current over here. I short circuit. Okay, so once again, we will have to ask ourselves, what is the easiest method to find I short circuit? Now, if you do nodal analysis and you apply nodal analysis at this node and this node, it's just going to be, it's not going to be possible to find I short circuit because you cannot, you will have one equation over here for this node, which will have this node value and this node value. But when you implement KCL here, then you're going to have the third unknown variable, which will be ISC, because you cannot really write ISC in terms of Ohm's law. We don't know that, I mean, the resistance is zero, right? So KCL is not really going to work on this circuit. So we'll have to apply KVL. And with KVL, actually, since this branch is a common branch that has current source, therefore we can apply super mesh in, let's call it, what do we call it? Let's say we call this mesh A. We have this A, so I'm not gonna repeat A. Let's call this, what do we call it? We call this, we have AB. So let's call this C, mesh C, and mesh D. Let's call this mesh C and mesh D. And let's assume our mesh C current is going clockwise, IC. And let's assume our mesh D current is going counterclockwise, ID. And again, these are totally random directions. And I short circuit is in this direction, so it's going in this direction. I short circuit. And then we can apply super mesh in mesh C and D, loop C and D. And then we can write one equation for the short circuit, the mesh with short circuit. And then of course our third equation is going to come from the current source, which will be, in this case, the current source I2 is equal to sum of IC and ID, but since IC and ID are opposite in the opposite direction, so it's going to be negative of the two currents, the sum of the two currents, IC and ID. So let's go ahead and write down the KVL equation. First, for the super mesh, apply in C and D. All right, when you apply super mesh in C and D, basically you are going in around the bigger loop. You're going around this loop right here. And then you're writing the KVL equation in the outer loop. So what will be the KVL equation for the outer loop? I'm just going to start with the negative sign over here. So negative V1 plus VR1. And then when I go here, let me do the assignment. So since the current is flowing in the direction of ID, that means you have the positive voltage here and negative voltage here. That's going to be VR3. And then for R4, uh, both ISC and ID are going from bottom to top. So we will have positive voltage here and negative here, VR4, because current, both ISC and ID are entering at the bottom and coming out at the top. If you change the direction of the current, of course, then you are going to take the current ID as your positive current. And if ISC is opposing that, then you're going to write down ID minus ISC. And in whichever direction ID is entering in R4, that direction you're going to assume to be positive, because whichever loop you're writing the KVL for, that loop current is assumed to be the positive current. So in any case, I'm going to write down negative V1 plus VR1 minus VR3 and plus VD and minus VR4 is equal to 0. And now Ohm's law, V1 is V1, so negative V1, VR1 is IC times R1, and VR3 is ID times R3, ID times R3. And we have VD. Now remember, VD is 2 times VR1 and VR1 is IC times R1. So I'm just going to write this down as 2 times IC times R1, and VR4 is ISC plus ID times R4. So plus ID plus ISC times R4 equals 0. So this is our KVL equation in the bigger loop C and D together. All right. Known values on one side, unknown values on the other side. So unknown values are IC, ID, and ISC, right? So I'm gonna first write down IC. So IC and R1. Actually, I have two ICR1 and ICR1, so 3R1. So 3R1. And then I have, that's only IC I have. So write this down then. 3R1 IC. 3 times R1 IC. So ICR1 and ICR. 3 ICR1. And now I'm going to write down ID. So I have ID over here, negative IDR3 and positive IDR4. So plus ID R4 minus R3. R4, oh, this was negative VR4. So that's going to be negative sign instead of positive sign. I made a mistake over here. That's negative sign. So negative ID plus ISC. So I have negative IDR3 and negative IDR4. So I'm going to put a negative sign here. Negative ID R3 plus R4. And then ISC, right? So ISC is right here, negative ISC R4. So negative ISC R4. And this is equal to V1 because V1 is going to go on the other side of the equation. So that's going to be equal to V1. And this is my equation 1. Okay, so that's my equation number 1. For equation number 2, I'm going to write the KCL in the loop with the current ISC. So let's write this down. Apply KVL, not KCL, sorry, KVL. Apply KVL in the loop with short circuit current. And once you do that, what you're going to get? So you are going to get VD and equals the voltage drop in this resistance, which is ISC plus ID times R4. So you have plus VR4 minus VD is equal to 0. So VD is equal to VR4. So VD is equal to VR4, which is equal to ID plus ISC times R4. So on the left hand side, I'm going to write down unknowns like I did in the question number 1. And that's going to be IDR4 plus ISCR4, and right hand side. Oh, actually VD is not, it has to be written in terms of 2 times IC times R1. So 2 times IC times R1. So we have all 3 currents present in equation number 2 as well. So I'm going to take this, of course, on the other side of the equation. So I have -2 IC times R1 plus ID R4 plus ISC R4 is equal to 0. And that's my equation number 2. And the final equation, since we have 3 unknowns and we have 2 equations, we have to write the final equation for the third unknown. And that final equation is going to come from the common branch where the current source is present. And that current source is equal to the sum of ID and IC, but in the opposite direction, because ID and IC are flowing in the direction opposite to I2. So I2 will be equal to negative ID plus IC. Also, I2 will be equal to negative of IC plus ID. And that's my equation number 3. So I have 3 unknowns and I have 3 equations. Let's go ahead and solve them using matrix inversion method. Let's go ahead and create our coefficient matrix A. And that coefficient matrix A from the first one is CLC. So clean it up a little bit. I'm not going to delete my variables because I'm still using the same variables. I'm just going to clear my screen. Okay, so from the first one, my A, the first row I see is 3 times R1. And then I have negative R3 minus R4. And then I have negative R4. And my second equation is negative 2R1, negative 2 times R1. And I have R4, and I have R4 again. And my third equation is negative IC, -1, -1, and then no short circuit current, so 0. So that's my A, and my constant vector on the other side of the linear equations. The first is V1, equation 1, equation 2, 0, and equation 3, I2. So V1, 0, I2. So this is my constant vector. So my unknown currents are going to be A \C, and the values of current are right over here. So let's go ahead and copy. So I'm just going to write this down. Solving 1, 2, and 3 simultaneously. We are going to get V Oops, what did I do? Let's scroll down. All right. Oh, it's plotting. I did it. Oh, I delete this and go back. I just want to capture this. So these are my three currents. This is IC and here. This is ID and here. And this is I short circuit. And here. So to calculate the R Thevenin from method number 2, we are going to take the ratio of V open circuit over I short circuit. We already calculated V open circuit. So the value is going to be R Thevenin is equal to V open circuit over I short circuit. Oh, that is, what was it? VA maybe. Yeah, it was VA, the variable that we used. So R Thevenin is equal to VA divided by I short circuit. Oh, I3, I did not assign the value, so it's simply I of 3 is I short circuit, I of 3. 1.8947. So that's my Thevenin equivalent resistance. Therefore, my Thevenin circuit is going to be A and B are Thevenin 1.89. I'm just gonna write 547, round it up to 5. And my B Thevenin was 17 point something, let's say 17.116. So 17.12 volt, round it up. So this is method number 2, in which if you do have a dependent source, you cannot eliminate these sources and combine resistance because you cannot eliminate the dependent source. So in method number 2, you put a short circuit between the nodes where the load is connected, and you're trying to find the Thevenin equivalent between those nodes. And then you calculate the short circuit current and take the ratio of the Thevenin voltage or open circuit voltage to short circuit current in order to get R Thevenin. Method number 3 to calculate the same R Thevenin is method 3 to calculate R Thevenin with dependent sources. So in this method, we remove all the independent sources. So open circuit the current source, only independent, remember, and short circuit the voltage. And then we insert a test voltage source or a test current source between the nodes AB where the load is connected, where you're trying to find the Thevenin equivalent. And then you figure out, the test voltage source or test current source, you already know the voltage. You're giving that voltage. You can take 1 volt if it's a voltage source, 2 volt, 10 volt, whatever. And then you calculate how much current that test source is supplying to the circuit. And then the R Thevenin is going to be the ratio of the test voltage source to the current that source is supplying. Or if you want to take the test current source, then the voltage across that test current source, you take the ratio of that voltage to the test current source, and that will be R Thevenin. So let me do it, and then it will make more sense than just verbally describing it. So the circuit that we had, I'm going to go ahead and eliminate the independent sources. So we had the voltage source over here, V1, that I eliminated. I shorted it. And then my resistance is here, R1. My resistance is here, R2. And then I have a current source that I'm going to eliminate. I'm going to open it. And then I have resistance R3 here. I have resistance R4 here. Or actually, I have first dependent source and then resistance R4, although it does not matter. Dependent source and resistor R4. Now dependent source you cannot eliminate. And then I'm going to insert a test voltage source over here. And that voltage source, I'm going to assign a voltage. So I'm going to say V test and is 1 volt. This is VD, R4, R3, R1. And observe, since this is R2, but since this is open circuit, so current is not going to flow through R2. So you can pretty much eliminate that branch if you want. We are trying to figure out this current coming out of the source. I test. How much is this current? Now, to calculate this current, if we know how much current is flowing here, let's call this I1, and how much current is, let's say, coming here, let's call this ID. Then if we apply the KCL at this node, let's call this node D. If we apply KCL at this node, then KCL equation is going to give us I test plus ID is equal to I1. Now, we already know the voltage of node D, so we don't have to apply a nodal analysis, by the way. We already know the voltage at node D. What is that voltage? It's the same voltage as the test, because test source is connected between D and ground. So the voltage at node D is the same as 1 volt. That means we can easily calculate current I1, because we know this voltage VD, and then you have two resistors R3 and R1. So we apply Ohm's law and we can calculate I1 equals VD over R1 plus R3. So that's VD is V test R1 plus R3. V test is equal to 1. And I1 is equal to V test divided by R1 plus R3. So 0.0833 or 83.34 milliampere. That's my I1. Don't forget that VR1 is here. And the dependent source, of course, it depends upon 2 times VR. So what is VD? 2 times VR1, and VR1 is negative of I1 times R1, because I1 is going from right to left, but VR1 polarity is from positive on the left and negative on the right. So the voltage drop in R1, which will be I1 times R1, VR1 polarity is opposite of that. Therefore, VR1 is 2 times negative I1 times R1. VD equals negative 2 times I1 times negative 1.667. 67. And now we know VD. It's very easy to figure out what ID is. ID is, again, you can switch VD, you can bring it down and take R4 on top if they're in series. So ID will simply be equal to VD minus V test. V test is going to be at this node, of course. VD minus V test over R4. That's going to be ID in the direction that I am showing the ID current. VD minus V test over R4. So ID is VD minus V test divided by R4. Negative 0.44. Negative 0.44. Okay. So now my I test current is therefore I test, which is equal to I1 minus ID. I1 minus ID, right? I test is I test plus ID is I1, so I test is I1 minus ID. So this current I1 0.5278 ampere. 0.5278. And now we are ready to calculate our Thevenin. We should put implies, which implies, so therefore, our Thevenin is equal to V test over I test. V test over I test. So our Thevenin is equal to V test over I test 1.8947. And to compare this value, we can look at method number 2, and we got exactly the same R Thevenin 1.8947. So this is the third method, which I would say in this case, it was much easier to use the third method in order to calculate R Thevenin. That is, we eliminated the independent voltage source and the independent current source, applied the test voltage source, and then calculated the test current. So this method, which you can see is like only 3-4 lines, was much easier than the second method for this circuit only. I mean, it's possible that second method might be easier for some other circuits. That is, if you short circuit the open terminals, you may eliminate, other stuff, and it turns out to be easier. But again, it all depends on the circuit. If we know both methods, we can just in our mind, we can kind of analyze which method might be easier to calculate the current value, either short circuit current or test current. And based on that, we can just go for that method. If I have to do it with either using method 2 or method 3, I will choose method 3 because it turns out to be, or it is going to be much easier just by analyzing the circuit and eliminating the independent current sources and voltage sources. So this is how you do it if you have dependent sources in the circuit. Remember, anytime you have dependent source in the circuit, open circuit voltage will be found exactly the same way as you did for in method number 1. However, R Thevenin, you cannot use method number 1 if you have dependent sources. If you do, your result is going to be incorrect. You're going to lose points, of course, if it is an assessment. So you must use method number 2 or method number 3 in order to calculate R Thevenin.